So, you know, our harmonic oscillator is, you know, what is it? It's a mass on a spring, essentially, and the little mass oscillates around. And if you were to sort of plot this in, and so the displacement away from the equilibrium position is Q, the coordinate. If you were to plot sort of Q and P, right, the space portrait of what happens to this thing, so P is the momentum. But classically, you know, so what would happen? You would, this thing oscillates back and forth, right? And as it passes through the equilibrium point, that's the place where you get the largest momentum. And so that's at 0 here. And when you have maximum displacement, that's when the mass turns around. So that's when the momentum passes through 0. And so as the thing oscillates around, it makes a little circle in phase space. With time. So there's a quantum mechanical way of thinking about this, and it's, again, taking advantage of complex numbers, right? So we could construct, classically anyway, a quantity, which I would call Z, which is a rescaled position. So this is QT, the position of it, plus I, put the momentum on the imaginary axis and rescale it. And so classically then, you could, of course, derive the equation of motion for Z, you know, do dz dt, and then you would apply Hamilton's equations for the harmonic oscillator. So out here you would get dq dt, and dq dt is nothing but, you know, p over m. That's dq dt. You know, it's x dot, it's the velocity. Velocity is momentum divided by the mass. And then here you would get square root of, you know, 2m h bar omega, and dp dt is, of course, Newton's law. That's, you know, F equals ma and whatnot. So that would give you minus m omega squared. This is k, the spring constant, times q of t. It's just, you know, minus kx. The restoring force. You know, this is just Hooke's law, or whatever you want to call it. F equals ma. So that's classically what it is, and you can see that this actually factors. You can factor out one factor of omega, and you can, what you get is minus I omega, and then the rest of the stuff that's left over is going to be just Z. Well, we can sort of see, you'll get, if you factor out a minus I, then over here you'll get an IP over square root of 2 h bar omega from this first term, and then over here you'll get a plus square root of m omega over 2 h bar q from this term. You factor out a minus I, you get a plus. There's 1 omega goes away, this m cancels with the square root of m, so you get this square root of omega cancels with the remaining omega, so you get this. So it's just minus I omega z of t. That's the differential equation classically that Z obeys. And so that's just sort of as expected. It's the solution to that is e to the minus I omega t, right? It's just, it oscillates around in a circle in the PQ space if you put P along the imaginary axis, which is what Z is all about. So it just makes a circle. Well, if you look at this form, this is exactly the same form as we had for the annihilation operator, which, if you recall, the annihilation operator was in terms of these rescaled coordinates, but now operators. This is quantum mechanics. Was I p hat, so all this over square root of 2. So it's just like this. This z of t is basically like the classical analog of the annihilation operator. Or, you know, if you want to be more particular, z of t is what the expectation value of the annihilation operator would behave like, right? You know, according to classical, according to the correspondence principle. So when, you know, the expectation value of A, that those things should behave, the expectation values of these rescaled coordinates should behave like the classical quantities. So it should behave like the Z. And you can check that it does. But so coherent states are basically the quantum mechanical version of this kind of circular motion, or at least trying to take advantage of that conceptualization of the harmonic oscillator in order to derive some interesting properties. So in particular, a coherent state, so a coherent state is an eigenstate of this annihilation operator. So it satisfies a Z like this. And it turns out that the spectrum of this operator is any complex number Z works. So the spectrum is really, you know, includes all complex numbers. And you can construct such a state. Remember, A isn't Hermitian or anything. It's so, you know, the spectrum could be all sorts of things. In this case, you can show that, you know, it's actually any complex number. It's continuous. And the eigenstates themselves are constructed from the energy eigenstates. And they don't have to be complete or anything. In fact, these are states that are over complete. I'll show you why in a moment. But you can show that the following actually is an eigenstate of the A operator. So it's a combination of all the energy eigenstates. And you can write it as this infinite sum, or if you want to interpret this as a Taylor series, then this can also be written as an exponentiated raising operator, right? Because the ends can be generated by applying the raising operator. And so taking care of this factor as well just gives you the following. And any complex Z works. So that's kind of interesting. And you can ask, like, what's the probability if you're in one of these eigenstates of measuring a particular energy level n, which of course is, you know, the following inner product squared. And this thing, if you dot this into n, what you'll find is that you'll get magnitude of z raised to the 2n power over n factorial e to the minus z squared. Just from dotting this into n, right, it'll pick out the one term in the sum, and then you square this whole thing, take the magnitude squared, you get this. And this is a Poisson distribution, which looks an awful lot like a Gaussian. So there's just interesting properties of it, and you'll explore it on the homework. So I just wanted to mention that you sort of study this in homework form. But that's kind of the idea, is that harmonic oscillator motion, describes a circle in phase space, and you can put it in the complex plane by introducing the z coordinate, and this thing basically behaves like the expectation value of the annihilation operator. So it's kind of interesting to study the annihilation operator itself and find its spectrum, its eigenvalues and eigenvectors. And what you find is that its spectrum is any complex number, and the eigenvectors are these z states, which are called coherent states. And they have interesting properties, which you'll sort of study for the homework. Any questions about that?
So you applied Taylor series, right? Like to get that tracing operator?
Yeah, it's just rewriting the sum in terms of the raising operator.
Can you like show the steps? Like how you got that 0?
Sure, I mean, it's this is square root of n factorial n, because each time you act with a dagger, it'll bring in a factor of n, for the next state over, so that this, if you do it n times, then you get, 1, 2, 3 multiplied out all the way up to n. So you get a square root of n factorial. So then this is square root of n factorial n. That's it.
Thank you.
Okay, so you'll study that on the homework. The other thing I wanted to mention is Bloch's theorem. It's important for condensed matter. Bloch's theorem, it's simple idea. You have a potential v of x that is periodic. And that means that there's a symmetry of this potential, right? You can translate everything by the period of the potential, and that doesn't change anything. So we can introduce a translation operator that just translates our wave function, say, by an amount a. Right, and we know that if this is a symmetry, right, if we can translate, we'll just assume that the the period here of the potential is a. Then we know that if this is an eigenstate, say in this problem, if this is a bound state, say for an eigenstate of this, the Hamiltonian associated with this potential, well, then the only thing that can happen to the wave function if we translate it is it picks up some phase. That's a possibility, because we know that the wave functions are only defined up to an overall phase. So NC is 1. So that's what's this? That's the symmetry. That's what it gives us. And so what else? Well, we can do a little better and put the entire system in some box that's periodic. And let's say the box is of size n, big N times A. And these will just be some boundary conditions we apply that'll make the problem easier to solve. And so if we put it in a box like this, we'll put explicit boundary conditions on psi over this whole box. So we're allowed to do that. And so what we'll say is that we'll assume periodic boundary conditions for the wave function across this whole box, which just means that if we apply the translation operator n times, then we better get back out the wave function again. So just putting the whole system into one big periodic box and forcing the wave function to be periodic across that big box. And then what the symmetry tells you of the potential is that because its potential is periodic in here, independent of what boundary conditions you put far away, independent of that, if you have a wave function here and you translate it to over here, because of the periodicity of the potential, it looks the same here or here. The only thing that can happen is that the wave function picks up a phase. So that's kind of the idea here. And so what this means is that this C number, this number C, whatever that phase is associated with translating the wave function by one unit of this periodic potential, that number must be a so-called root of unity, right? Because if you raise C to the n, which is what this translation operator does, then you should get out just one. So C raised to the nth power is one. So it's a root of unity. And so C must have the following form, must be an exponential of 2 pi I m over n, where m is 0 plus or minus 1, and so on, all the way up to plus or minus n minus 1 over 2. And we can define, and we can call this I k sub m, right? And k sub m would be 2 pi m over n over a. So we can assign an associated wave vector by dividing by a, the periodicity. So we can define these wave vectors km. And so then what that means is, now we know what the C number is. It's just one of these guys. We know that our wave function, our eigenstates of this periodic potential, well, they can be labeled by these K's. There might be, for any particular value of C, there might be an associated wave function, because there's these possibilities for C. That's just all we know so far. And what we know is that if we take one of those that's labeled by one of these K vectors and we translate it, the wave function, then what we should get is e to the I ka psi of k x. That's the general property that the eigenstates, the eigenfunctions of this periodic potential should have, that when you translate them, you pick up a phase, and the phase has the following form, that's e to the I k, some wave vector times the periodicity, the wavelength of the potential, and the k's are given by just these guys. So what you can do then is write the wave function in general as e to the I kx times a periodic function. Now this function now is really periodic. So it satisfies u of kx is equal to u of kx plus a. And now you can use this as a kind of ansatz, if you want, for solving the Schrodinger equation. Right? You can plug this in as a form for the Schrodinger equation, for the solution of the Schrodinger equation. So that's what we can do. And the other thing to note is I'll write down what the k's are again, just from up here. It's 2 pi m over NA. And we see that as n goes to infinity, right, what happens is m goes to infinity. These m's, of course, are 0 and plus or minus 1 and plus or minus 2 and so on. So up to, about n over 2. So as n goes to infinity, this wave vector starts to become like a continuous variable that kind of lives between negative infinity and infinity. So that's something to keep in mind as we make the periodic box bigger and bigger. The number of k's that we can have gets larger and larger, and eventually it becomes a sort of continuous label for our wave functions. And the label just tells you how the wave function translates when we move it over by 1 unit of the potential. So that's what the symmetry gives us of any periodic potential. And so then what you can do is you can stick this into the Schrodinger equation. You can take the Hamiltonian, act with it on, psi of k, and just sort of see what happens. You get minus h bar squared over 2m, the kinetic energy, 2 derivatives with respect to x, acting on e to the I kx, the periodic bit. Then, of course, you have this, the potential, which is periodic. And all of this has to be equal to the energy. So we're looking for bound states. And so what happens here, right? What happens is here these 2 derivatives hit both the e to the I kx and the uk. Hit both of these things. So what you get minus h bar squared over 2m. And here you get minus k squared uk. I'll drop the as a function of x, right? It should be obvious. Plus, I'm going to factor out this e to the I kx business. So then these 2 derivatives, they'll hit this guy. So you'll get that. Then you'll get cross terms, right? It's 2 derivatives, so it can hit these 2 guys, and that'll happen twice. So you get 2 ik dx uk. That's hitting the exponential once and the u once. And then you get, of course, the potential bit. And all of that, you get the factored out e to the I kx. And that's, of course, all equal to the energy. So these guys cancel, and you get a differential equation now for the u of k's, which you can now, and now you know that the u of k's are actually explicitly periodic functions. So you can apply that as a boundary condition. So it might not look like you've gained much by rewriting the Schrodinger equation this way, but you did, because these UKs now are, they're explicitly periodic. And so all you have to do is solve this differential equation. Let me rewrite it, I guess. E UK is equal to minus h bar squared over 2m. 2 derivatives with respect to x minus I h bar squared k over m. 1 derivative, that's the cross term. And then you have the potential, v of x, and then you got the u of k. So it's, a second order equation for u. You can now solve this for u. For a fixed k, and then the whole solution, all of the eigenstates of the system, because we know how the wave functions are related to these periodic solution. So that's kind of how it goes. And you do a lot more of that in solid state physics, but so we won't really talk about it very much. The reason I wanted to bring it up is because it uses some of the things we talked about, right? That physically distinguishable states can only differ by a phase, right? Complex number with magnitude 1. So if you have some symmetry in your potential, say, where it looks the same, whether you translate, by some A, then the wave function associated with, bound states of this thing has to satisfy this property. Then we do a kind of clever thing where we put the whole thing in a big periodic box, and that's you can do something else and do something else to the wave function far away, but it's convenient to do this periodic box, which just fixes the boundary conditions far away. And those two things are enough to kind of give you the form of the energy eigenstates. They have this particular form that they're labeled by a K, which as you make the periodic box bigger and bigger takes on any value from negative infinity to infinity. And it has this phase out front, e to the ikx, and it's multiplied by a pure periodic function. It's periodic in the potential, right? It's periodic. Why is this cool? Is because this thing is periodic over just one of these small periods. So you only have to solve Schrodinger's equation inside this box, right? That's what this is telling us, because then the Schrodinger equation just reduces to a differential equation that lives just inside one of those little periodic units of the potential. And you solve this using whatever differential equation methods you want, and then you get the full solution for the full periodic potential. So that's the idea. That's the idea of Bloch's theorem, is that you can couple this, you can solve for the Schrodinger equation inside one of those little periodic units, and then Bloch's theorem tells you what the form of the wave function is everywhere else. That's the basic idea, but I really won't really do much more related to that. I also wanted to bring this up because it illustrates, just like the harmonic oscillator, we sort of jumped back and forth between coordinate representation and the energy eigenbasis. You can actually do a similar thing for periodic potentials, or any kind of potential really. So you can imagine, say you had some periodic potential. What if you didn't really want to go through this business of using Bloch's theorem and solving inside the little periodic units? You might try to guess what the structure of the spectrum is. Like, what are the energy eigenstates, and what do they look like? And you can imagine if the potential is sort of has large barriers between these little wells, you can imagine the bound states could at least be constructed by looking at just what would happen inside one of these wells, right? Similar to this idea of solving the Schrodinger equation inside just one of these periodic blocks. You can imagine that there would be a wave function associated with a kind of bound state inside one of these potential wells. And that's kind of what you can do, is you can label these wells, for instance, 0, let's put a 0 on here, and then there's an infinite number of them. So in principle, there's one at 0, and then you would label the ones left or right of it, plus or minus 1, this would be 2, and then out here you get minus 2. And you can kind of guess what the effective Hamiltonian would be in this basis, instead of doing the coordinate representation in terms of wave functions. You can do it in terms of the basis that you would make from bound states inside each of these wells. You could call them n, like this. This would be a bound state associated with each of these little wells. And then you might guess that there would be some energy, bound state energy, associated with the particle sitting in one of these wells, and that would give you a term like this. This is the sort of diagonal part of the matrix, right, in this basis. So these would be the energies of the individual little bound states in each place. And then you would have some kind of tunneling, right, describing the interaction between, say, adjacent wells. And in that case, you could introduce a hopping term between adjacent wells. So you could look at this Hamiltonian, and in the case where the potential wells are kind of deep in this periodic potential, this would be a good approximation in this different basis of what you would get if you were to solve it exactly for an explicit form for this potential v of x. Yeah, so I talk about this form more in the notes. This is sort of like a phenomenological description of a periodic potential, so you can check that out if you're interested in that formulation of it, or if you're interested in condensed matter. This is, I guess, a famous model in condensed matter for electronic band theory. So I would check it out if you're interested in that, but I won't really go over it very much more. Maybe we can do a recitation on it if people are interested. But I did want to show you a little bit about periodic potentials. And so same sort of things we do with the harmonic oscillator apply to any kind of potential. The idea of using, so the important thing here is the idea of using symmetries in order to constrain the form of the wave function. And the other important idea is that solving Schrodinger's equation is sort of independent of the representation you use. You can think about it as a differential equation in terms of the wave function, or you can think about it as a matrix in terms of some basis of, say, constructed by some bound states, for instance. So in the harmonic oscillator, we thought about the actual energy eigenstates forming a basis for the harmonic oscillator. Here we can think about in the periodic potential as the as bound states inside each well, forming a basis from which we can write down the Hamiltonian in this fashion. So that's a little bit of a flavor, I guess, of how these things connect up to more complicated problems. But any questions about that? It's a little bit vague, but it's intentional because this is really would be a topic of a solid state class. Okay, well, very good.
Wait, there was you got a chat in the chat.
Oh, I got a chat.
Yeah.
Okay. Isn't this the Hubbard Hamiltonian? Oh, this is the tight binding model, I guess it's called. Hubbard Hamiltonian is more complicated. So we're doing you'd say single particle kind of quantum mechanics, right? We think about a particle living in some potential with a kinetic energy, and that's all the kinds of problems that we're going to look at for a while. So this Hamiltonian is just the same as the one I started with. It's just a single particle and you living in periodic potential. So what are these states? These end states. What are these end states? Just the particle living in well 0, or maybe it's living in well 1, or maybe it's living in well 2, right? There's just one particle. So that's the idea. Yeah. And the other thing I wanted to mention before we move on to entanglement is, now let me just clear this, I guess. Is what happens in 3 dimensions. Not much. It's just all your derivatives with respect to x turn into gradients. So it's not any different. You have your canonical commutation relation, and now your x coordinates have multiple components like x, y, z, and your p becomes a vector. So there's x, y, z. There's a component of p along x, y, z, and they all commute unless they're pointed along the same direction, in which case you get just the usual canonical commutation relation. So it's all the same. And your Hamiltonian now, you have to combine all of the components x, y, z together and sum up all the momenta, and then your potential might have a more complicated form that depends on the actual vector of coordinates that you have. But it's not any different really. It's just like the difference between single variable and multivariable calculus. So really no difference. And you can write this in coordinate representation. Your p becomes, instead of 2 derivatives, you get a Laplacian. And your potential depends on the coordinate of your wave function. Your wave function now, depends on, instead of just x, depends on x, y, z, and but you're still solving some differential equation, except now it's in multiple variables. So instead of an ordinary differential equation, it becomes a PDE, a partial differential equation, and but it's still the same conceptually. There's no difference really. Another important point is this probability current that we were looking at now becomes a true vector that you can construct, but it's still the real part of h bar over im psi star, and now it just becomes the gradient of psi. So it becomes really a vector because you take the gradient of the function, it points along the gradient of the wave function. And of course, if we wanted to jump back and forth between position and momentum, we could. You just have, instead of the 1-dimensional Fourier transform, you have the 3D Fourier transform, where you integrate now over 3D space, but it's still the same. You still take the wave function and Fourier transform it like this. Yeah, so that's why we don't really talk about 3D very much, because conceptually it's not that different. You just have to solve a multi-dimensional differential equation instead of a 1-dimensional one. But usually the kinds of problems you solve, you will use some symmetry, like you assume that you have spherical symmetry, in which case everything, you can use spherical coordinates to write down this Laplacian. Or you assume that the dimensions are independent of each other, so you look for solutions to the Schrodinger equation that are products of wave functions along the x, y, and z directions. And they might be labeled by the appropriate solutions along those directions. So you look for states like that. You can take this as a ansatz and plug it into here and for a particular potential and go from there. So let's say you could do particle in a 3D box, right? You would just ensure that the boundary conditions are satisfied independently along 3 directions, say. So yeah, so that's why we didn't really talk about that very much. In Sakurai, it's a lot of time spent developing notation just in order to do the multivariate case, but not really necessary. We'll go back to this in the second semester when we do 3D scattering, and we'll look at spherically symmetric potentials quite a bit when we do the hydrogen atom, I guess. So we'll go back to this, but have no fear. You do know it. Studying the 1D case doesn't really hurt you very much. It's just conceptually it's the same thing, really. This is the main thing that you have to remember, that the Hamiltonian is an operator, right, on a Hilbert space. In the Hilbert space, we could use different kinds of bases to represent this operator. It can act on, we can think about it in position representation, in which case it acts on, wave functions. And the Hilbert space is, the space of all square integrable functions. Or we can use another basis for the Hilbert space. We can say use the energy eigenstates of the potential, in which case, our operator will act on those energy eigenstates, which we looked at, for the harmonic oscillator. So that's the idea, and it's the same in 1D or 3D. It doesn't really change that aspect of it. That's the important part, is this kind of connection. Any questions though? So that's kind of wave mechanics. You'll practice it in homework 4, of course. And we'll go back to this 3D stuff in the second semester. Yeah,
The
any questions?
energy is additive here, right?
Sorry?
The energy E, it's the sum of energy nx, ny, nz.
Well, it depends on the example. For which example are you talking about?
Oh, not in particular. I was just asking about this 3D case when the energy, the total energy is the sum of energy in all directions. Well,
no, it's hard to say what if it is or isn't. Depends on the potential and the particular problem of interest, right? So this is a differential equation just like the 1D one. The only difference is that now this side depends on 3 coordinates. So it's a partial differential equation. You have to, now your boundary conditions are going to be different, right? You have boundary conditions in all 3 directions. And this is still just a number. So it's still whatever the energy is, it's just, you're still trying to solve this eigenvalue equation, which is what this is. So depending on the particular system, if it's decomposable that way into the orthogonal dimensions, then maybe you could interpret it as a sum of, the energies along. If it's like a particle in a box, you can, sure. But in general, no. In general, you have to solve this and see what values of the energy that you get. Just like you would for a bound state problem in 1D. It's very similar.
Okay.
All right, more questions? Okay, great. There's more in the notes on this, but we won't really talk much about it. So it's for those who are interested, there's more in the notes. I do the particle in a box for 3D. So I would check the notes if you wish. But I don't really think conceptually, it's not that important. And we'll do more in the second semester for 3D stuff. All right, any more questions about wave mechanics, just in general? Anything about it? All right, so I mean, the next thing we're going to do is talk about entanglement. And I mean, really what we're talking about is composite systems. What happens when you have two Hilbert spaces? Say you had two systems that you're trying to think about together. Say you wanted, you had one of these spin 1/2 guys that we looked at when we studied qubits, and say you wanted to combine it with some other spin 1/2. How do you think about two of them simultaneously as an entire system? And in Sakurai, this idea in Bloch, if you're following Sakurai or something, he doesn't really talk about it this way. Why? Because one way to talk about it is just talk about combining angular momentum, which is what we'll do later. But we're going to talk about just combining systems in general. So again, the idea is, here is chapter 6 in Bloch. For those of you following Sakurai, I don't really have a good way of telling you what to read there, because a lot of the concepts are embedded in the angular momentum chapter. Why? Because a lot of the interesting parts of angular momentum is when you want to add two different angular momenta together. So you wanted to add the spin angular momentum to the orbital angular momentum. Your electron has the intrinsic spin, but then it's also living, in some atom, in some orbital. And you want to know how to add the angular momentum of the orbital to the, angular momentum associated with the intrinsic spin. How do you do that? Well, you would talk about the spin 1/2 part of it, right, combined with the orbital part. And then you would ask, how do you treat that as a composite system of, two spins? The spin 1/2 part and the orbital part. So that's, but you can think about it generally. It's just, how do you combine Hilbert spaces? How do you combine the spin 1/2 Hilbert space with the spin whatever space of the orbital angular momentum space? So that's the idea. And that's why we're going to talk about it in this general way, and because we know a lot about Hilbert spaces. Well, let's talk about that. So what do? You take a Hilbert space for one system, and it might have some dimension n, and you want to combine it with another one, system 2, which might have some other dimension m. And the idea is pretty simple. It's, that you have vectors that live in either one of these. So if you want to think about a composite system, well, then you just say that maybe you can think about these systems as pairs of states. You specify which state it's in for the first Hilbert space, and which state it's in for the second one. And in order to avoid writing curly braces everywhere, this is often denoted as a tensor product state, where you say what it is in the first Hilbert space, you add this little tensor product, and this is what it is in the second one. But it's just like writing it as a little collection of vectors. So that's the notation. And this now lives in a tensor product space, which is a combination of the first Hilbert space and the second one. But it's nothing out of the ordinary. You're just specifying which vector you're in for the first space and which vector you're in for the second one. And you have to order them, so you can't flip these around. That's bad. You have to make sure you maintain the proper order, because this was always refers to the first one and this is always refers to the second one. So you can't flip them around. So that's something to be aware of. The order matters.
Yeah, I know that tensor, you can't do that, but now, and the one that you're doing, just to make sure we have it right, is the Hilbert space 1, you said superscript n, and then it would be like tensor Hilbert space 2 superscript m.
Yes.
2 n's.
Yeah. Yeah, sorry, this is N, and this is M, yeah. Is that what you're saying?
Yeah, I just want to make sure. That's what I thought, and I know you can't with tensor with general relativity. The same thing we were taught about tensors. They're not, flipping.
Yeah, so, right. And so now you can do, what we usually do, which is, let's write down a basis now for this tensor product space. What would it be? Well, you would take the basis of the first space and the basis of the second one and just look at all combinations like that. And of course, it would be orthonormal. Because you would just dot the individual pieces together, and you would get an orthonormal piece for the first Hilbert space and an orthonormal piece for the second Hilbert space. And so you could do a basis decomposition in principle of any state, phi1, phi2, which would be now a sum over, the first Hilbert space basis and the second Hilbert space basis. You would have individual coefficients for each of those basis elements. So you have, Cn complex numbers, Dm, and you'd have like that. So you could do a basis decomposition. Now you just have to sum over both of the basis sets. And in principle, there'd be a coefficient for each one, like that. So you can prove that this definition doesn't hurt things, like you maintain linearity and all those features that we normally have for a Hilbert space. What else? And what else is that everything is fine so long as so the question is, are all states of your composite system expressible like this? The question is, are these all the physical states? Right? Say we had some composite system of like 2 spin 1/2, right? Can we always write the state of that system as something like this, where we specify the ket of the first spin 1/2 guy and then the ket of the second one, and then that's it. That's the state of the whole thing. And the answer is no. There are states that you can write down that are not like this, and those are so-called entangled states. But we do have a postulate. These are special in the following sense. We introduce a kind of fifth postulate of quantum mechanics concerning composite systems. And this fifth postulate states that two interacting systems So yeah, let me say one more thing. So if two systems are not interacting, if 2 spin 1/2s are not interacting, then we could specify, each states, for each of those subsystems, we could just specify the ket, right? If they're totally disconnected out here, then yeah, sure, I could just say, well, this one I found in state phi1 and this one I found in state phi2. And so sure, I can then combine. The combined state is just the tensor product of the two. But if they're interacting in some way, then that's not necessarily true. But there is something that is true, which is given by this postulate, that even if they're interacting, the two interacting systems will have a space of states given by H1, H2. So what it means is that even though we might not be able to say definitively if, this guy is in ket 1, is in state, with phi 1, and this one is state phi 2, it might be possible that, so even though we can't say that, it's still going to be, whatever the state is, it's still going to be a part of this Hilbert space, this tensor product Hilbert space. And I forget how this theorem's actually, or how this, what the kind of mathematical underpinnings are of this postulate, but it's something that you just assume. So what it means is that we'll be able to use this as a basis for the two composite systems. But it's just that the states, the composite states, don't necessarily factorize in this way, where we can interpret it as a tensor product between two kets. And I'll show you examples. I'll show you examples when we do spin 1/2 in a moment, where this is made clear. It might not be obvious, how that works right now, but we'll see. But the point is that we introduced this tensor product of Hilbert spaces, and this is the relevant space for the composite system. And this postulate just states that, when you have two systems, we can think about their combined state as some vector inside this tensor product of Hilbert spaces for the first system and the second system. So that's it. That's all we know for now. And that's, the content of this fifth postulate. We can also do operators. Operators, you have to be careful and specify which piece of the tensor product you're acting with. So the operators kind of have to be extended, right? You have to tell me that, you're acting on the first piece of the tensor product or the second piece. So whenever it acts on one of these states, you have, the following. You have to act with the operators individually. And of course, you can construct matrix elements. So this is for an operator that's a tensor product of A and B. So what this means is this part acts on the first system, the A, and then this part acts on the second one. And this is how it works. If you wanted to construct matrix elements, it's the same as this inner product that we had before. You will just have matrix elements for the first subsystem, right, multiplied by the matrix elements of the second one. So that's how tensor product operators work. But it's possible that you have some operators that don't break up this way, right? That kind of mix the different vectors in your tensor product space, not in this kind of independent way. And in that case, the matrix elements for a general operator that cannot be written like this, well, then it would have just matrix elements, right, that don't factorize like this into a product of individual matrix elements. It would just, you would have matrix elements for each possible value of n prime, m prime, and n and m. So you like double the number of indices that you have for the matrix. If we're talking about identical subsystems, of course. And often you want to act on just one piece of the tensor product state. So you might define operators like this, where you take well, let me do some other notation. So often you would look at operators that just act on one subsystem, in which case it's sort of implied that you're tensor producting with an identity for the other piece. And maybe you write a little 2 here to indicate that it's the identity for that second subsystem, right? Or like this. So this acts on system 2, right? And this acts on system 1. So that's kind of the idea. And of course, if you wanted sort of the matrix elements, say, of this guy, then you can write those down too. What would this be? Well, the A acts on this first bit, so that just gives us the matrix elements for the A operator, and then this part is the identity, so that must give us just elements along the diagonal, so this gives us a delta, like that. So it's all kind of, it's straightforward. It's, if things decompose into a tensor product, then you just make sure if the operators can be written as, you know, these tensor products, then you just apply the first bit to the first part of the tensor product state, and then the second bit applies to the second one. And then that's it. And then any inner products just get multiplied together like that. So that's the idea. And now, so let's do any questions about the sort of general scheme here? I think the only part I was vague about is this idea of, are these all physical states? I'll give you an example of what I mean by this.
I think an example will help us. Sure.
Yeah, but I just, does anyone have any questions about just the like notation, I guess?
For the tensor products, is there an identity for that? Like an operator tensor product with something else can equal that operator back?
Um,
So I don't know if there's one. I would have guessed the identity matrix, but I guess it's not.
well, the identity for the whole tensor product space would be, you know, the tensor product of the individual identities, right? So that's the identity for this acting on any one of these states. Would just spit me back out the state.
Okay, but I guess, is there any relation that's, you know, like a tensor product I is equal to A?
A tensor product I is equal to A.
Yeah.
So it's a good question because we really have to think about the spaces now, the dimensions of the space. So when I write A tensor product I, what is this object? It's not, it's got dimensions of the first bit times the second bit. So it's, if A has dimension, if A is an n by n matrix, and this is a m by m matrix, then the whole thing is an nm by nm matrix. This is a very big matrix.
Gotcha.
This is, well, I don't know what you would mean by this. This would be an n by n matrix, right?
Yeah.
So there's no way to make these match. So that's not actually possible because they have very different dimensions. This tells you how this acts on these states, right? Phi 1, phi 2. So it tells you how to act on both of them. Here you do nothing, and here you apply A. Whereas this guy, I don't know, but that would act on just the first Hilbert space, right?
Yeah, you're right.
So it doesn't, they have mismatched dimensions.
Gotcha.
So it's important to keep in mind because in physics, a lot of times when you have like operators that act on just one subsystem like this, they often drop this tensor product notation. And that's very bad mathematically speaking, because they're like totally different objects mathematically, but physicists just kind of hand wave through this. But you know, you'll see a lot of things like, say you have two spin 1/2, one's like spin up down, you have a state like this. You'll often see in physics books things like you're measuring the spin component along the z direction for like particle 1, right? And then,
yeah.
but this is not, that's not right. I mean, the only way this is right, the way you would interpret it, right, is what's really happening is you're measuring the z component for the first spin, and then you're doing nothing to the second spin. And that's what what's really going on. So
Gotcha.
yeah, so it's worth it to see the math once, to just make sure you're aware of when people sort of sweep it under the rug, which happens a lot. Okay, but yeah, we're gonna do spin 1/2, two spin 1/2 particles, quite a bit. That's sort of the two of them. And instead of doing the whole tensor product business, we're gonna, instead of doing like these guys, that's annoying. We're just gonna put them next to each other. So this is a tensor product of the first spin 1/2 being spin up and the other one being spin down. And so we can write a basis now for the whole tensor product space, right, of H2, H2. This is a tensor product of two-dimensional Hilbert spaces. So what's the total dimension? It's 2 times 2 is 4, right? So there should be 4 basis vectors for the whole tensor product space. What are they? Well, you can just construct them using the Z basis. It's just all the combinations of spin up and down for the 2 particles. Just as I mentioned up here, more generally, right, that the base is just all combinations of the 2 bases for the individual systems. Okay, and again, just as before, we're gonna do this kind of hand wavy thing where we'll define spin measurements for either particle 1 or particle 2 as these kind of tensor product operators like this, which is a shorthand notation. So for instance, if we have S1Z acting on, say, the up, what would this do? Well, it would measure the spin component of the first guy, which would give us an H bar over 2, and do nothing to this one. So you would get H bar over 2, up, up. You can apply them in succession, for instance. You could apply this and this on up, up. What would you get? You would get this guy would first pick up an, let me do a better example, I guess. Yeah, this is where we'll leave off. I know we're sort of running short on time. So yeah, I'll just do this quick example of this notation. Say we're doing an up-down state. What would this do? So this would first act on the second one, right, and give us a minus H bar over 2. So you get minus H bar over 2, S01Z acting on up, down. Now I have to do this. This acts on this first one, gives us a plus H bar over 2. So you would get minus H bar squared over 4, up, down. Kind of do them one at a time, and just remembering that you're actually, acting on the individual spins each time you do that. So the next thing we'll do is we'll talk about, in general, the state, we know that the states of the individual spins, we could write them as linear combinations, right, of spin up and down. We sort of saw that already when we did the qubits. What we'll ask ourselves is it always possible to consider the state of a composite system of both spins at the same time as some tensor product between phi 1 and phi 2, where phi 1 and phi 2 are just some arbitrary kets associated with the individual Hilbert spaces? And the answer will be no, you can't always do that. Even though any general state, any state can be written in terms of the basis of 4 eigenkets, any arbitrary state inside the tensor product space can be written as, I don't know, lambda 1 up, right? Plus lambda 2, because it forms a basis. So this is certainly true. But we'll see that even though these 4 guys form a basis for our Hilbert space, it's not the case that any composite state of the 2 spin 1/2 can be written like this, where it's a tensor product between 2 kets. And we'll see that. We'll see that explicitly. Might not seem obvious, but it's true. You can't. So we'll see that. We'll see that. It's not obvious right now. It's not obvious because you kind of think, well, there's 4 unknowns here and there's 4 unknowns here. Maybe I can just rewrite things and these are all just the same thing, but they're not. You'll see. It doesn't always work. All right. Does that kind of make sense, at least where we're going with it?